This is the tangent function tutorial. The tangent of an angle results from the coordinates of a point on a line tangent to that of the unit circle. And these are the properties of a tangent function. Now first I'll show you what a tangent function looks like and then we'll discuss the properties. So I'm going to first bring in that unit circle that we referred to and the definition of the tangent function. Now like we said, the tangent of an angle results from the coordinates of a point on a line tangent to that of the unit circle. So for this demonstration, I'm only going to use all the coordinates in the first quadrant of the coordinate plane. So I'll go ahead and get rid of everything else here. Next I'm going to draw in two lines that are tangent to that of the unit circle because like we said, the tangent of an angle results from the coordinates of a point on a line tangent to that of the unit circle. So what we want to do here is draw in an angle to refer to. So I'm going to go ahead and create a 30-degree angle in standard position. Now you know how to find the values of this point right here on the unit circle. I'm going to teach you how to find the tangent value to that line. So the value of that point on the unit circles, you know that the cosine is the x-coordinate, so root 3 over 2, so the cosine of 30 degrees is root 3 over 2, and the sine value of 30 degrees is 1/2, that's the y-coordinate of that point on the unit circle. Now the tangent is actually this value in purple here, that purple point over on the line right here, that line tangent to the unit circle. So the tangent value that we're looking for isn't even on the unit circle here, it's on the line tangent to that of the unit circle. Now obviously, since that line is tangent to the unit circle, the x value of that tangent point is going to be 1. Because any line that is tangent to a circle like that, as it intersects the circle, it intersects it at a 90-degree angle. So it's going to go straight up from that x value of 1. So we know that our x-coordinate of that tangent point is 1. And the y value of that tangent point can just be derived by dividing sine over cosine. When you do that, you can take a look at our sine value here, which we knew was 1/2. We're going to divide that by the cosine value, which was root 3 over 2. Now that value, if you put it into a calculator, is 0.577. That's the equivalent value if I just drew a dashed line directly over here to the y-axis, we would have gone vertically up 0.577 units. So that's the y distance here traveled when that 30-degree angle in standard position intersects a line tangent to the unit circle. So that's where we get the idea of a tangent function, because we're talking about a line tangent to our unit circle. So the easiest way to find that tangent value there is to just divide the sine value of that angle in standard position by the cosine value of that angle in standard position. So for example, let's find the tangent of a 45-degree angle now. So our 45-degree angle drawn in standard position is going to look like this. We're going to draw one ray of that angle in standard position along the x-axis, and it joins the other ray at the origin of our graph here, so that vertice occurs at the origin, which makes it an angle in standard position. So here's our two rays, and we want the tangent value. So if that ray were to continue on, we want the value here as it intersects a line tangent to the unit circle. Well, we obviously know that the x value of that is 1, because it's on that tangent line. Now to arrive at the y value, all we want to do is take the sine value of a 45-degree angle here, so root 2 over 2, and divide that by the cosine value of that 45-degree angle, which is also root 2 over 2. And you know that anything divided by itself is 1, so root 2 over 2 divided by root 2 over 2 is simply 1. So if you were to put in the tangent of 45 in your calculator, it would return a value of 1. It's just the sine value divided by the cosine value. Now let's take a look at the properties of a tangent function. So the standard tangent function is y is equal to a times the tangent of b theta. Now the parent tangent function is simply y is equal to tangent of theta. Remember, there's a difference between the parent function and the standard function here. the parent function is just going to be a tangent graph without any transformations. The transformations could occur in that a and b value. That's going to refer to the amplitude and the period in cycles, respectively. So, we know that theta is in radians and b must be greater than 0. The interval of one cycle is from negative pi over 2b to pi over 2b, and pi over b is the period of the function, and there are vertical asymptotes at the end of each cycle. So let's go ahead and look at some problems dealing with tangent functions. In the first problem here, I'd like you to use the graph on the left to solve for each of the following values. Let's begin by solving for the value of tangent of negative pi over 3. Well, we're dealing with a negative, so we're going to go to the left of the origin here. And we can see that this value right here is negative pi. So negative pi over 3 is going to be 1/3 the distance. So I'm going to go ahead and divide up this negative pi distance to the left of the origin into 3 pieces. 1, 2, and the last third piece being that negative pi right here. So I cut it into pi thirds, and we're doing the tangent of negative pi thirds. So if you just travel downwards at this negative pi over 3 value here, you intersect the tangent function right here. Now if I were to travel across to our y-axis here, I'd arrive at roughly negative 1.73. And that's the tangent value of negative pi over 3. If you were to go back and look at your unit circle, pi over 3 correlates to a 60-degree standard position angle. Because it's negative, you'd go clockwise around the unit circle. So from 360 back down to 300 degrees. And if you entered the tangent of 300 degrees into your calculator, you'd get an approximate value of negative 1.73. Now let's take a look at the second problem, tangent of pi over 4. Well, we know that this right here is pi over 2. So pi over 4 is going to be half that distance. Half that distance is approximately right there. So if you were to travel up to where it intersected the graph, and then travel from there over to find your corresponding y value, you'd see that the corresponding y value here is 1. And the tangent of pi over 4 is the same as the tangent of 45 degrees. And the tangent of 45 degrees is exactly 1. So that's how you can use a graph to find the values of a tangent function. Now let's look at another problem. In this problem, I'd like you to determine where 2 asymptotes occur for the following function and identify the period of the function. So our function here is y is equal to the tangent of 2 theta. I'll go ahead and bring back in the properties of a tangent function for you to look at. Let's begin by determining the period of our function. Now remember, the period of our function is pi over b, and we know that the b value occurs right before our theta. So for this function, our b is 2. So to calculate our period, we're just going to divide pi by b, which in our case is 2. So that's the period of this particular function. And remember, the period is the horizontal distance in which each cycle repeats itself. Now the interval of one cycle is from negative pi over 2b to pi over 2b. So in our case, negative pi over 2 times 2, because our b value is 2, to pi over 2 times 2. 2 times 2 is 4, so the interval of one cycle is negative pi over 4 to pi over 4 units. So let's go ahead and draw these in. Here we have our standard tangent function, which is passing through our origin here at 0, and each cycle is occurring between negative pi over 4 right here and pi over 4 right here. Now our vertical asymptotes are just going to occur at the end of each cycle. So I'm going to go ahead and do those vertical asymptotes at negative pi over 4 and pi over 4. Those asymptotes are the lines that this tangent function cycles are going to approach but never touch. Now let's take a look at another problem. In this problem, I'd like you to sketch the graph of the following tangent function and the interval from negative 2 pi to 2 pi. And our function is tangent of negative 3 over 2 pi times theta. So remember that the coefficient before our theta here is our b value. So for this problem, b is equal to negative 3 over 2 pi. Our period is defined as simply pi over b, so pi over negative 3 over 2 pi. So I'm just going to invert and multiply the denominator of our fraction here, so 2 pi over negative 3, and this becomes 1. So pi times 2 pi is 2 pi squared, and 1 times negative 3 is negative 3. So this is going to be the period of our function, 2 pi squared over negative 3. And I'm just going to put that into a decimal form here. So 2 pi squared over negative 3 is roughly negative 6.6. Now also keep in mind that the interval of one cycle ranges from negative pi over 2b, so over 2 times our b value, which is negative 3 over 2 pi, to positive pi over 2b, so 2 times a negative 3 over 2 pi. So essentially the interval of one cycle in our graph is from negative pi over negative 6 over 2 pi to positive pi over negative 6 over 2 pi. So we again want to just invert and multiply the denominator here to solve for our actual interval. When you do that, you see that our interval ranges from pi squared over 3 to a negative pi squared over 3. So this is the interval of one cycle of our tangent function. So now we're ready to draw the graph. So if you plug in pi squared over 3 in your calculator, you'll see that that comes out to an approximate value of 3.3. So our graph is going to range from negative 3.3 to positive 3.3 for each cycle, which is exactly half of that period, negative 6.6. We went 3.3 in each direction. So our asymptotes are going to occur right there at pi squared over 3, so negative 3.3, and 3.3. So we drew those straight lines up as our asymptotes. So just like with sine and cosine functions, tangent functions are easier when you've done a lot of practice. So I recommend going through all the practice problems you can and getting used to establishing what your asymptotes are, your interval cycles, and your periods for tangent functions. Learn how to draw graphs forward and backwards and just practice as much as possible to get through these sections. They're really not too bad once you've done them, but you got to put a little bit of time into practicing them. Now that you've seen all the standard trigonometric functions, let's go ahead and take a look at the reciprocal trigonometric functions. Reciprocal trigonometric functions are just as they sound. They're the reciprocal of our standard trigonometric functions. So if you recall, our standard trigonometric functions are cosine, sine, and tangent. So you'll notice that the reciprocal of cosine is secant. Secant is 1 over cosine theta. And the reciprocal of sine is cosecant. Cosecant is 1 over sine theta. Now cotangent is the reciprocal of tangent, so it's 1 over tangent theta. Now let's take a look at how the graphs behave for each of these reciprocal trigonometric functions. We'll begin with secant. Secant is derived from 1 over cosine. So on the left here, I've prepared your standard graph of cosine. This is the graph of cosine theta, the parent function, so y is equal to cosine theta. Now notice that each cycle occurs over a distance of 2 pi, or a period, because remember our horizontal distance on the x-axis for every one cycle that repeats itself inside of a trigonometric function, that's considered to be the period of the graph. And if you look to the right here, this is the reciprocal of cosine, so 1 over cosine theta gives us this graph, which is the graph of secant theta. Now notice how with secant, instead of having a nice gentle cosine curve, we actually have these parabolas, and they alternate positions. A positive parabola, then a negative parabola, then a positive parabola, and so on. Also notice that each of these parabolas occurs within a period of pi. So now instead of having a period of 2 pi for each cycle, each of these cycles occurs within a period of pi. And the boundaries of that period are denoted here with these asymptotes, these lines going straight up. Now remember, these are the lines that these parabolas are going to approach but never touch. Alright, so that's what a secant curve looks like. Let's go ahead and take a look at a cosecant curve. And remember, cosecant is the reciprocal of sine. So on the left here, I've gone ahead and drawn our regular sine function. This is the parent function of sine, y is equal to sine theta. Again, notice that for every period, for every one cycle that goes by, we cover a horizontal distance of 2 pi. However, notice that on the right here, on our cosecant graph, each of these parabolas still only covers a period of pi units. And again, our parabolas alternate from positive to negative, positive to negative. Now also notice that in the parent function of cosecant, our parabola is off-center of the origin. It's to the right and to the left of that y-axis. But if you recall with our secant parent function, one of those parabolas happened to be split by the y-axis. So in terms of their parent functions, that's how you can identify which is a secant and which is a cosecant. The parent function of the secant graph has a parabola that's bisected by the y-axis, whereas the parent function of the cosecant graph, which is what we're looking at now, doesn't ever touch the y-axis. Now remember, a translation later can shift these and it could end up on the y-axis, but the parent function cosecant graph that we're looking at here will never touch the y-axis. Now let's go ahead and take a look at the cotangent function. Alright, so again I've drawn our tangent function here on the left and our cotangent function here on the right. Now notice that our tangent function has a period of pi units. And we have that typical S-shaped curve for the tangent function. In science we call that a sigmoidal curve. You'll also notice that we have an asymptote every pi units along the graph. Also notice with the parent function of the tangent function, so y is equal to tangent theta, you have one of those curves passing right through your origin here. Whereas if you look at the reciprocal function, the y-axis is an asymptote and a curve will never pass through it. Now you'll also notice with our cotangent function that our period is still pi units, the distance from one cycle to the next. But notice that the direction of our curve has changed. Now we're coming down from the left and passing over to the right, whereas before, on our tangent function, we were coming up from the left and heading over to the right. Alright, now that you've had a chance to observe some of the changes in these reciprocal trigonometric function graphs, let's take a look at some of the problems that you'll be dealing with. Let's begin with a little simple calculator work. Evaluate the following expressions and give your answer as a decimal rounded to the nearest thousandth. Let's start with the problem on the left, the secant of negative 105 degrees. Now remember, secant is 1 over cosine theta. I like to remember the difference between secant and cosecant as that the beginning letter of secant and cosine, which it deals with, switch. So secant is 1 over c and cosecant is 1 over s. Notice how the s and c change positions. They're the opposite or the reciprocal of each other in both these graphs. So secant is 1 over cosine theta. So secant of negative 105 degrees can be written as 1 over the cosine of negative 105 degrees. Now you want to put it just like that into your calculator, 1 divided by the cosine of negative 105 degrees. And the answer you get is negative 3.86. Your calculator doesn't have a reciprocal trigonometric function button. There is no secant button or cosecant button or cotangent button. You actually have to type it in just like that, 1 over the regular trigonometric function that it is. So in the case of secant, 1 over cosine of that degree you're looking for, in our case, negative 105. Again, remember that your calculator must be in degree mode to do these problems. If you're in radian mode, you're going to get the wrong answer. So now let's take a look at cotangent of 45. To take the cotangent of 45, we just have to take 1 over the tangent of 45 degrees. And since the tangent of 45 degrees is 1, we have 1 over 1, which is still 1. So the cotangent of 45 is 1. Now notice that our answer here are decimal answers, so these are approximate values. Now I'll teach you how to solve for the exact value of a reciprocal trigonometric function. Determine the exact value of the following expressions. So let's begin with secant 30 degrees. In order to solve for the exact value of these reciprocal trigonometric functions, we want to take a look at our unit circle, so I'll go ahead and bring one in for us to look at. In this case, we're being asked to find the secant of 30 degrees. Now remember, the secant is 1 over the cosine theta, and in this case, theta is 30 degrees. So what you want to do is draw your angle in standard position, or consider which of these angles is 30 degrees in standard position. So that's what our angle would look like. Now remember that cosine theta is the x value here from our unit circle. So cosine theta is really root 3 over 2. So I'm going to write our problem as 1 over root 3 over 2. Now remember, we can't have a root 3 over 2 or a fraction in the denominator for that matter. So what I'm going to do is invert and multiply. So I'll multiply by 2 over root 3. And this now becomes 1. So we multiply directly across when multiplying fractions, so 2 times 1 in the numerator is 2, and root 3 times 1 in the denominator is root 3. So the exact value of secant 30 degrees is 2 over root 3. Now remember, we can't have a root in our denominator, so we're going to take that 2 over root 3, and we're going to multiply it by a root 3 over a root 3. So on top we have 2 times root 3, which is simply 2 root 3. And on bottom we have root 3 times root 3, which is the square root of 9. And the square root of 9 is 3. So our answer becomes 2 root 3 over 3. That is the secant of 30 degrees. Now let's take a look at our next problem, the cotangent of 45 degrees. Now remember, cotangent of 45 degrees is the same as 1 over the tangent of 45 degrees. And tangent of 45 degrees is the sine of 45 degrees. So here's our 45 degrees. Our sine is here, the y value, root 2 over 2. And our cosine is here, root 2 over 2. So tangent is sine divided by cosine. So what we have is 1 divided by our sine, root 2 over 2, divided by our cosine, which is also root 2 over 2. Now notice when you have something divided by itself, so in this case root 2 over 2 divided by root 2 over 2, that's always 1. Anything divided by itself is 1. So this really translates out to be 1 over 1. So we know that the tangent of 45 degrees here has a value of 1, like we just figured out above. So the cotangent of 45 degrees is equal to 1 over 1, and anything again over itself is 1, so the cotangent of 45 degrees has a value of 1. Now that we've done a little work with degrees, let's go ahead and take a look at some problems that involve radian measures. I'd like you to evaluate the following radian measures. Let's begin with the cosecant of pi. Now, like previously, these are straightforward calculator work problems. However, for these problems, you want to make sure that your calculator is in the radian mode. So this first problem, the cosecant of pi, can be written as 1 over the sine of pi. And you'll want to put it in just like that into your calculator, 1 divided by the sine of pi. Now the sine of pi is 0 because if you remember from your unit circle, pi is 180 degrees around your circle, and the sine value of that is the y-coordinate. And you happen to be lying on the x-axis when you go 180 degrees around the unit circle to a value of pi, which means that your y-coordinate is 0. So the sine of pi is 0. So this problem is actually 1 divided by 0, which you cannot do. So this is one of those few problems that you're going to find that has an undefined answer. You want to get used to what that's going to look like in these because occasionally you'll come across one, and you want to have some confidence in dealing with them that you have found the right answer. So the cosecant of pi is undefined. Now let's take a look at the cotangent of 3 pi over 2. So we'll write that out, the cotangent of 3 pi over 2. And remember, the cotangent is just the reciprocal of tangent. So 1 divided by the tangent of 3 pi over 2. And you'll put that in just like that to your calculator. 1 divided by the tangent of 3 pi over 2. Make sure that your 3 pi over 2 is in parentheses. Now if you took a look at your unit circle, 3 pi over 2 is 270 degrees. And 270 degrees is straight down on the y-axis. So if you went out to the edge of the unit circle there, straight down on the y-axis, your coordinate point would be 0, -1 because you'd be 0 on the x-axis and -1 straight down. And when you're doing tangent, you're taking the sine, so the y-coordinate, and dividing it by the x. Well, if the x-coordinate is 0, what you'd be trying to do is take -1 and divide it by 0. And again, you cannot divide by 0 in this case. So once again, your answer for this problem would be undefined. Alright, so now that we've seen a couple undefined examples, let's take a look at one that's going to work out to a number. Evaluate the following radian expression. So in this case, we're looking at the cosecant of 2 pi over 3. Remember, the cosecant of 2 pi over 3 is going to look like 1 over the sine of 2 pi over 3. Now put it into your calculator just like that, 1 over sine 2 pi 3. So if you put it into your calculator as 1 over the sine of 2 pi over 3, what you'll get as an answer is 1.15. Now remember, your calculator has to be in radian mode for this to work. Now let's take a look at graphing some of these reciprocal trigonometric functions. What we're going to do is graph the following functions in the interval from -2 pi to 2 pi. So what you want to do for this graph is go into the y equals location on your calculator and type in y equals cotangent of 3 pi over 2 times x. Remember, x in your calculator can represent theta while graphing. When you do that, your calculator is going to return a graph for you that looks just like this. Notice all these vertical asymptotes along the graph. And remember, your calculator doesn't have a cotangent button, so when you're putting it into the calculator under the y equals, what you have to do is 1 divided by the tangent of 3 pi over 2 times x. Remember that. That's how you have to enter these reciprocal trigonometric functions everywhere on your calculator as the actual reciprocal of their original trigonometric functions. So if you were to enter the problem over here on the right, y is equal to cosecant 3 times theta, how do you think you'd enter it into your calculator? Well, you'd have to do 1 divided by sine of 3 times x. Remember, theta is going to represent x, and to make a cosecant, we need to do 1 over sine. So what you'll see is your standard cosecant graph here. If you didn't get graphs that look like this in your calculator, make sure that you're in the correct mode, which for these problems is your radian mode. Lastly, let's take a look at one simple algebra problem that deals with reciprocal trigonometric functions. What we're going to do is evaluate the following expression. If the cosine of theta is equal to 7 over 4, find the secant of theta. Well, remember that the secant of theta is simply 1 over the cosine of theta. And you know that the cosine of theta is 7 over 4. So what we're going to have is 1 divided by 7 over 4. So again, we're going to invert and multiply, or multiply by the reciprocal, which is 4 over 7. So 1 times 4 is 4. This becomes a 1 now, and 1 times 7 is 7. So the secant of theta, if cosine theta is 7 over 4, the secant of theta must be 4 over 7. So you may have noticed in this tutorial that a lot of our work with reciprocal trigonometric functions must be done on our calculators, which is kind of a nice break from all the math work that we've been doing in dealing with regular trigonometric functions.